Imagine controlling a robot arm with incredible precision, making it move exactly where and when you want it to. How do engineers achieve this level of accurate, smooth motion? Calculating joint space velocity is absolutely crucial for understanding and controlling how a robot arm moves. It defines the rotational or translational speed of each individual joint, and this directly impacts the end effector's overall movement, allowing for precise manipulation. The core principle behind this calculation lies in the relationship between individual joint velocities and the robot's end effector velocity in what we call Cartesian space. This intricate relationship is elegantly described by the Jacobian matrix. Think of the Jacobian as a sophisticated translator, transforming the angular or linear speeds of each joint into the linear and angular velocities of the robot's tool or gripper. Each element within the Jacobian quantitatively represents the influence of a specific joint's motion on the end effector's velocity components in a given direction. Understanding this matrix allows us to predict the end effector's speed and direction based on the individual speeds of the joints, and, conversely, to determine the necessary joint speeds to achieve a desired end effector motion. To practically calculate joint space velocity, you first need to determine the robot's forward kinematics, which precisely maps joint angles to the end effector's position and orientation. From this forward kinematics, you then derive the Jacobian matrix, which is essentially a matrix of partial derivatives of the forward kinematics with respect to each joint variable. Once you have this Jacobian, you can relate the vector of joint velocities to the vector of end effector velocities through a straightforward matrix multiplication. This means if you know your desired end effector velocity, you can simply use the inverse of the Jacobian to solve for the required joint velocities, enabling very precise motion planning and control. The Jacobian is not just a tool for calculating velocity. Its rank and singularity properties are vital for understanding a robot's manipulability and avoiding configurations where the robot effectively loses degrees of freedom. These problematic configurations are known as kinematic singularities. Being able to quickly compute and analyze the Jacobian helps engineers design more robust control algorithms and ensures safer, more predictable robot operation, providing a real-time snapshot of the robot's kinematic capabilities. Mastering the calculation of joint space velocity through the powerful mathematical tool of the Jacobian matrix gives you a fundamental and indispensable insight into a robot's movement mechanics. This understanding is essential for designing effective control systems and ensuring your robot moves exactly as intended every time.
If you love robotics, like, subscribe, and keep building with us.